Truth tables show the output of a logic circuit. They let you predict what a circuit will do before you wire it up. The idea is simple. You list out every possible input combination, and then for each logic gate output, you make a column for it and list the outputs. You do this for all the outputs within the circuit until you arrive at the final output of the whole thing. So let's do an AND gate with two inputs, column A and B. Each input can be 0 or 1. So let's list these inputs in the header, A and B, and then we have one output, and let's call that C. Right, so here's the inputs, and there's the output. We need to figure out all the input combinations. So we'll start from 0 and we'll count upwards in binary as we go down the rows. So it'll be 0, 0, 1, 1, 0, and 1, 1. Doing that guarantees that you don't miss any cases. So always start from 0 and count down in binary. An AND gate only outputs 1 if both the inputs are 1. So in your 4 rows, the output is 0 for 0, 0, 0 for 0, 1, 0 for 1, 0, and 1 for 1, 1. For an OR gate, the output is 1 if at least one input is 1. So for 0, 0, it's 0. This one is 1, 1, and 1. For an exclusive OR gate, the output is 1 if either OR of A and B are 1, only if either OR of them exclusively both on, it'll be a 0 again. So for the first case, 0, 0, none of them are on, so that's 0. This is going to be 1, this is going to be 1. In the last case, they're both on, so that's 0. Truth tables aren't just for single logic gates though, so you can use them for combinations of gates. The method never changes. You write out all the input combinations and then you calculate the output for each row step by step. For example, so you have 3 gates wired together. Inputs A and B go into an OR gate, giving an intermediate output X. Inputs C and D go into an AND gate, giving an intermediate output Y. And then those two inputs go into a final AND gate, giving the final output Z. So this is our example logic circuit here. To make the truth table for it, let's first list all of the inputs and then the outputs. And remember, it's not just going to be Z, it's intermediate states too. X, Y, and then finally Z. So those are all outputs of the gates. So to make the truth table for that, first we're going to compute X from A and B, then compute Y, and then Z using the last AND gate. Doing it in that column order is the easiest way to avoid mistakes because you're always using the values you've already worked out. Starting from 0 with these inputs and then counting upwards in binary to get all of the possible in combinations. Right, so there's all of our inputs if I haven't stuffed anything up. Righto, so let's go row by row and calculate the intermediate outputs. X is the OR of A and B. So in this case, A and B are both 0. X is going to be 0. Now let's go through and just compute A or B the whole way down. It's 0 for the first 3 cases, and now we have all of the rest of the cases are 1. So an OR out of that is always going to be 1. Y is an AND gate, inputs C and D. So if both C and D are on, it's going to output a 1. So there's 0. See, if there's zeros anywhere in C or D, then it's just going to be 0. So it's only 1 for those 4 cases. Righto, let's take these two intermediate states and AND them together to get Z. So now we're only looking at these two columns. 0 and 0 is 0, 0, 0. We're only going to be 1 if they're both 1. So here, here, and here. Righto, there's the output. Now, if we've taken a circuit and used Boolean algebra to simplify it to a simpler equivalent circuit, let's verify if those two circuits have the same functionality using the example in the logic gates video. Y equals A and B or A and not B. So this is the equation. Y is A and B or A and not B. How that looks is this. Inputs A and B, they go into an AND gate, or A and not B. There's Y. Right, so we've basically taken the input A and B, ANDed them together here. Then we have the second statement, A and not B. So we take the same inputs, A and B, we not B first, and then we AND those two together, the not B and the A. And the output of that goes into this big OR gate that takes those intermediate states. So we can simplify it by making this. Let's make it this is J and this is K. So A and B, the output of that is K. A and not B, the output of that is J. And now we just have Y equals K or Y. So K or J, which is the output of those intermediate states. So the truth table for that is going to look like this. Start from 0, count it out in binary. We compute K and J. So K is the product of AND. We know that that's only going to be 1 if they're both on. J takes B not and A, ANDs them together. So we basically take these, instead of just looking at it and ANDing them together, we have to invert B first. I'm just going to draw a little helper function here. And now we AND these two. Right. So J is going to be 0, 0, 1, 0. Righto. Now let's OR these together. K and J. 0, 0, 1, 1. That's the output. Our simplified circuit in the Boolean algebra video was Y equals A. Now if we take this table, we can see here's the values for A and this was the output Y. And it definitely does equal just A. So this big circuit that we've just drawn in, and this big equation simplifies down to Y equals A. In the Boolean algebra video, we show how that works, and in this video, we've just proved that it works. If these videos aren't enough and you want one-on-one time, rescue with content in a lab or exam preparation, I'll also offer private tutoring. Leave a comment or apply through my website. There's a link in the description of this video, and I'll let you know if I can help.